presented by Caltech.
So I want to continue with the interference and diffraction discussion. The book discusses the Michelson interferometer, so I want to just say a little bit about that here, and we're going to have a demonstration of it on Tuesday. And so the idea is that we have, we have some source, light source. We say frequency f. It's propagating along, and we hit a beam splitter with it. So it's a piece of glass maybe, or quartz or whatever, with the front surface half silvered, partially silvered, so that a beam can be reflected from it, and a beam can be transmitted through it. And so the transmitted beam has some refraction, which we'll discuss. So it goes at a slight angle. That's pretty a big angle that I've drawn, but it goes at some angle due to the refraction in the glass. We saw that with our little laser before that I showed the four beams through, that the light kind of shifted over. So there's a transmitted beam that goes like this, and we let it hit a mirror. So this is just a mirror. And it hits the mirror, and it bounces back. And when it bounces back, it follows the same path. This is half silvered, so some of it will reflect. Reflect down like that, and refract. And we let it end up, get absorbed in some kind of detector down here. So that's the beam that gets transmitted through this. For the other beam, we also put a mirror up here. And we could just let it hit the mirror and come back, but to try to equalize the thing that happens to the path along the two directions, we notice that this beam, as it goes through the glass here, comes back, goes through a second time, and then the bounce here goes through a third time. So if we just had this one come up and bounce back and go through it, it only goes through one time. So we just put another chunk of glass here, such that it will go through once, twice, 3 times. So it goes through a piece of glass 3 times as well. So both beams go through the same amount of glass, or quartz, or whatever it is that the stuff's made out of plastic. So this beam goes up here and then bounces back and goes back down. And so the light path, there are 2 paths that the light can end up going through to get down to the detector, and so there can be interference. In particular, if the phase of the light that comes back here and down, and the phase of the light that goes up here and down isn't the same, they will interfere in some way. So let's do a little analysis of that. Let's let L sub 1 be the total path length from source to detector via, so let me call this let me call this mirror M1 and this mirror M2. So via M1 and L2 equals the total path length from the source to detector along M2. And so what we're going to care about is the difference in these path lengths. So we assume that we're just transmitting a, say, monochromatic wave. So we've got a laser as our source maybe. It's transmitting at one, it's emitting at one frequency. So if we take the path length and define it to be, say, L2 minus L1, the change in the difference in path lengths, L2 minus L1, if that's equal to some integral number of wavelengths, lambda equals the speed of light divided by the frequency is the wavelength. In this case, then the two waves, the two paths, arrive in phase at the detector. And superimpose or interfere, that just adds the superposition constructively. So we call that constructive interference. When two waves are coming in phase, one wave has a phase like this, the other wave has a phase like this, and they just add. The other path. And so, if there are no losses along the way, that gives an intensity at the detector equal to the intensity from the source, assuming we're not losing anything along the way. On the other hand, if delta L is some number of half wavelengths different, that's not an even number of half wavelengths, then you have a situation where these waves interfere destructive. So one wave might have a phase like this, and the other one is just the opposite. It's a half wavelength alpha. Draw it down here. And the two add up and give 0. The detector. And so this provides a useful device for measuring various things. It's a device for measuring difference in path length. If you say put some material in there that maybe has some index of refraction you're trying to measure. So if you put something with some index of refraction that you're trying to measure in the path, in one of these paths, say in that path there, then the speed of light will be different along part of that path and along the other path. and that will change the relative phases. So if you originally have things constructively interfering, and you find that if you put this material in, you end up with 0 at the detector, you know you've changed the phase by some number of half wavelengths. And if you work it out carefully, then you can actually measure, say, the index of refraction of something that you put in the path. And so this is a technique that's used to measure indices of refraction. We'll have a homework problem on that, so you can try it out. Okay, so we'll play with a Michelson interferometer on Tuesday. I just wanted to make sure you mentioned it. Have any questions on that? So back to our more general discussion of EM waves. So again, we're in some uniform isotropic static lossless medium. Keep things as simple as possible for the beginning of the discussion at least. And there's no sources. Rho is equal to 0. Current density is equal to 0. So charge density equal to 0, current density equal to 0. So there are no charges, no free charges. There may be a material that's built out of atoms, and that's fine. But it's just, we haven't added some additional free charge somewhere. The material we average over all the atoms, the electrons and the protons that are bound together in the material using the electric permittivity and the magnetic permeability. So I've rewritten Maxwell's equations without the D and the H. Again in SI units. So del dot E equals 0. I wrote down del dot D equals 0 before, but I could, with these assumptions, I could just use E here and del dot E is equal to 0. Divergence of the magnetic field is equal to 0. Of course, del dot E is equal to 0 just because I said rho is equal to 0. I mean, if there were some charges around, I'd have to put a rho over here. But I'm assuming there's no charges. Del cross D is equal to minus d by dt, the time derivative of the magnetic field. And del cross B is equal to the dielectric constant, the dielectric permittivity times the magnetic permeability times the time derivative of the electric field. So if this were in a vacuum, this would be epsilon naught and mu naught, which are just two constants that are, well, they're actually derived constants nowadays, I guess, in SI units. So, okay. So, I want to think about waves. I know that, I know light is reaching us and it somehow behaves like a wave because I can do things that look wave-like with it. Light is just electromagnetic waves, so I should be able to get waves out of these Maxwell's equations. So let's try. Let's consider this curl equation. Del cross E, so the curl of E is minus the time derivative of the magnetic field. I'm going to take the curl of both sides. Why do I do that? Well, okay, just bear with me. I'm looking kind of ahead. I want to get, say, a wave equation for the electric field. So I need to get the electric field over here. I know if I take the del cross B, I'm going to get the electric field over there. So maybe that's going to work out. So let me take the curl of both sides. So let's see, so okay, del cross E is equal to minus del cross d by dt of B. Of course, this side's easy, that's minus d by dt of del cross B, and I know that's equal to del cross B is minus epsilon times mu d squared by dt squared of E. So at least that side looks like the second time derivative that appears in the wave equations we're used to. What's this this del cross thing? So let's just recall the vector identity. Or rederive it again if you don't remember it. This says if I take a vector cross with that vector cross another vector, so it's like this kind of. We know what that gives. Is that, so you can check it out and make sure that that's right. So I can apply this identity to the curl across the curl of something, just keeping in mind that these are derivative operators and they operate on everything to the right of it. So you just have to be a little careful, but you can use vector identities like this to work with the del operator. And in this case, everything's ordered in a nice way such that I can conclude that del cross E is equal to, so E is the E and U is del, is just the gradient of del dot E minus del dot del, which is just del squared, Laplacian, on E on E. Okay? But Maxwell's equations tell us that this is 0. And so therefore I have minus Laplacian of E is equal to, where was it? Minus epsilon mu second derivative of E. Or I just rewrite this without the minus signs and bring it all over to one side. I get del squared E minus epsilon mu d squared by dt squared on E is equal to 0. And that looks just like our old friend, the wave equation. And so it's a wave equation we can read off the speed. So whatever appears here is 1 over v squared. So with speed v is equal to 1 over square root of epsilon times mu. So if we were in a vacuum, we know that electromagnetic waves propagate with the speed of light. Well, what we define it to be. Speed of light, well, yeah. Electromagnetic wave, okay. Travel at the speed of light. So v would be the speed of light if we were in a vacuum. And so if we're not in a vacuum, v is in general slower, so we'll never faster, it's in general slower, and so we can use this to actually define what we mean by the index of refraction. So n is somehow the ratio of the square root of epsilon mu to the square root of epsilon naught mu naught. So the electric field satisfies a nice simple wave equation. In fact, the same wave equation, if you start, so I opted to start with del cross E equals minus dt by time derivative of B. I could have started with that equation and taken the curl of both sides, and that would give me the same exact wave equation, but for the magnetic field. So both the electric field and the magnetic field satisfy the wave equation. Notice that it's a wave equation on a vector quantity, which we haven't really dealt with before. These fields are vector quantities, but they satisfy a wave equation. And so we can write what we call the plane wave solutions to this wave equation as electric field as a function of position and time is equal to some magnitude and direction, E naught, times our phase vector, E to the I. So now it's a wave vector k dot x minus omega t. And so you can plug this in here and find that it actually satisfies the wave equation. Well, okay, we have to relate k and omega. We'll do that. And likewise, v of x and t is equal to some complex number in general from e to the I k dot x minus omega t. So both satisfy the same equation. And so now let's just think about this a little bit more, okay? Of course, from the let me bring it down so you can see what's on. That's enough. Now, when you take the second derivative of this with the del squared term, that's going to bring down minus k squared. And the frequency term is going to give omega squared. And so you're going to get k squared is equal to omega squared over v squared, where I substituted in the v for v squared for the epsilon mu. So you can try that explicitly yourself and make sure that works. Okay. So k squared is let's consider divergence first. going back to Maxwell's equation, one of Maxwell's equations, del dot E is equal to 0. I can do the same thing with del dot D, but let's do it explicitly with del dot E here. So del dot E of x and t, so I just plug in this field, is equal to, well, okay. So I take the dot product as E naught x times d by dx plus E naught y d by dy plus E naught z d by dz. So I've done the dot product with this vector out front, and it's going to operate on e to the I k dot x minus omega t. But now, d by dx, say, of e to the I k dot x is just going to be I times kx times e to the I k dot x. Because this is just kxx plus kyy plus kzz. And so this is like a product of 3 exponentials in each one of these, and only one of them depends on x. So you have an I kxx, you bring down the I kx thing, you take the derivative. So therefore, del dot E is equal to I times, so this will bring down an IKX, this will bring down an IKY, this will bring down an IKZ. So we get an IK dot E naught, K dot E naught, e to the I, K dot X minus omega t. That is, and this is equal to 0 by the Maxwell's equation. And so therefore, K dot E naught must be equal to 0. So the direction of propagation is perpendicular to the direction of the electric field. Likewise, I could have started with del dot B equals to 0, and I would find that K dot B naught is equal to 0. So the conclusion So remember that K is a vector pointing in the direction of the wave propagation. That's the direction the wave travels in. So that means that E, the electric and the magnetic fields, are both perpendicular to the direction of the wave. That is, electromagnetic waves, at least with these assumptions, are transverse waves. In the sense that the wave is going in this direction, the electric field may be pointing this direction, so electric field is oscillating up and down like this while the wave's traveling along. And the magnetic field is doing the same thing, whatever direction it's taking, but it's all, they're always perpendicular to the direction of the wave. Let me consider the equation, go back again to Maxwell's equations, and consider del cross E, which is minus d by dt of the magnetic field. I can take the derivative of the magnetic field over there, the time derivative of it, it just brings down an I omega. And with a minus I omega that cancels that, so I get an I omega times D. But del cross E, that brings down an I k cross E. Just do the same kind of manipulation, write out the del cross E in a similar way to this, except now the direction is going to be k cross E instead of k dot E. And so k cross E, B goes like k cross E. So B and E in particular are orthogonal. So B and E are orthogonal to each other, and they're orthogonal to the direction of the wave. And so therefore we have something like this. The wave might be traveling in this direction. The electric field might be in this direction. So it's oscillating back and forth. Okay. And then by the right-hand rule, we have to get B is like K cross E. So K cross E. So B is like this. So they form a mutually orthogonal set of three vectors. And so the wavefront that contains the electric and B fields is just propagating along the K direction. So there's more discussion of this in the note on electromagnetism, a little more detail there if you want to refresh yourself on any of this. So there are a number of interesting phenomena that come up with electromagnetic waves as these vector field waves. Let me consider first refraction. So we're going to violate our original assumptions. We said every space is uniform and isotropic and so forth. So what we're going to do is we're going to put another material into our space, and we're going to ask what happens. So within the material itself is uniform and isotropic and all that, and the rest of the space is uniform and isotropic and so forth. So everything we said holds separately in these two regions, and then it's just a matter of what happens at the boundary of these two regions that's of interest. So working out the boundary conditions on these electric and magnetic fields takes a little bit of thought, and the electromagnetic note actually does this in some detail. But we can do some things without having to go through too much math. So let's consider say a light wave of frequency omega. It's impinging at some angle, which we'll call theta, on a flat boundary between two media. So we might have chunk of material. And we're throwing a wave at it at some angle. Let's see, I'll take this to be the angle theta. And what happens? Well, okay, what are these media? So let's suppose the region out here has an index refraction N1, and this medium has an index refraction N2. That's really sufficient to specify what's going to happen here. Okay, that's all I need to know. I mean, that's all that appeared in the wave equation was this epsilon times mu, which is just related to, which is because one over the velocity squared, which is the velocity of c over n. Okay, so the difference between these two media is basically that the speed of the wave is different in the two media. So I could come along with wave fronts that look like that. These wave fronts are separated by the wavelength. Okay, so this is lambda 1. I call it lambda 1 because it's the wavelength in medium 1. And that wavelength is going to change in medium 2 because the speed is different. So the frequency stays the same, but the speed is different. Let's see. So what are the speeds? V1 is equal to c over n1. Of course, if n1 happens to be just a vacuum or air, air is essentially a vacuum, so it depends on what kind of problem you're working on. If you're comparing air with a piece of glass, then the air is like a vacuum. Then V1 would be about C. Okay. And so this is equal to omega divided by K1, the wave number in medium 1. So K1 is just the magnitude of the K vector in region 1. Material 1. And likewise, V2 is C over N2 is omega over K2. And so let me work that out a little bit. I'm going to assume, for the sake of illustration, that the N2 is bigger than N1. Just because I'm going to make a drawing that's going to assume that. So let's see. So K2 is related to K1 by K2 is N2 over N1 K1. And the wavelength, lambda 2, is related to lambda 1 as the inverse of this, N1 over N2, because K is 2 pi over the wavelength. So the wavelength in region 2 is going to be less than the wavelength in region 1, assuming N2 is bigger than N1. So if N2 happens to be 2 and N1 happens to be 1, the wavelength in region 2 is half of the wavelength in region 1. So let's see. So what happens? So I need to I'll try to draw things a little more carefully. So this distance is lambda 1 here. I get into that second region, I'm going to have something that's half the wavelength that it was out here. If say N2 is twice N1. How do I draw that? Something's got to give, okay? I can't just all of a sudden start drawing something with half a wavelength here because I've got to match these. I've got to match the wavefront. So my wave has to effectively turn in order for you to match this wavelength condition. So let's see. So it's going to turn something like this. Let me see how well I can draw it. Something like this. So that this is, okay, I'm terrible, but here, something that's going up here. And so in the material, the wavelength is half. So I tried to draw it to be like a half, but this is, so this distance here is just wavelength and medium 2. And you can see the wavefronts are going in a different direction now. They're going somehow in a different direction. And of course, once they get back out here, they have, you know, on the other side it's N1 again. And so now here they end up with the original wavelength. So our wave has effectively changed angle by some amount that we have to figure out in the second region. So let's try to figure this out. Let me draw a blow up of the transition region. And let's see, suppose we've got the first wave is coming in at some angle. So I've rotated the whole diagram so that the transition between N1 and N2 is vertical on the board as opposed to tipped. So the incoming wavefront is now tipped. So this is the incoming wavefront. Okay, and then it's got some wavelength, so it goes up to, say, here. So these are two wavefronts of the incoming wave hitting that transition at an angle. And let's see, if I were to draw a perpendicular to the interface, then the incoming wave is coming in at angle theta. This distance is lambda 1. And let's see, so this will be angle theta 2, I guess. So this is the incoming wave. Now the outgoing wave twists by some angle. So there's the wavefront. There's this wavefront as it passes through the material, it comes out there. Okay. And then, okay, down here again, of course. So this distance here. So this distance here is lambda 2. So there's a theta, let me call this theta sub 1 here, and this angle theta sub 2 here. It's changed direction, so the incoming angle is different than the outgoing angle in the material. So let's see, so I have I have a triangle here, and I have a triangle here. They have a common side, and I know two of the other sides. And so lambda 1 is just whatever this side is. That's the hypotenuse of that triangle. It's the hypotenuse of both triangles. It's the hypotenuse, so it's lambda 1. That common side is lambda 1 divided by sine theta 1. The other side, the other triangle with this common side, so I put in the equal sign here because it's the same length that I'm calculating, is lambda 2 divided by sine theta 2. And so we get, in terms of the index of refraction, lambda 1 goes like 1 over n1, lambda 2 goes like 1 over n2, so we get n2 over sine theta 1 is equal to n1 over sine theta 2, or we can write this as n2 sine theta 2 is equal to n1 times sine theta 1. So this is the law that gives you the angle of refraction as a function of the incident angle. And you know that as Snell's law probably. And so we've worked that out just by knowing a little bit about waves and the speeds. There's a different derivation of this, the equivalent, ultimately, derivation of this in the notes that you might be interested in. So that's not the only thing we can do with these waves. Since they're vector waves, they're transversely polarized, but we still have a degree of freedom. And so that brings us into the notion of polarization. And the electric field could be pointed this way or that way for a wave going that way. So we have two possible choices. Those are the two possible polarizations. So let's suppose, for the sake of illustration, that our wave vector is along the z direction. E sub z is a unit vector in the z direction. I could just write it as, I wrote it as z hat before, so let me be consistent with the way I wrote it before. Okay. Then E is in the xy plane. And we can, as long as we keep an xy plane, where it points in that xy plane is arbitrary, so we can make an arbitrary polarization for E. Just by considering the linearity of the problem, we can take linear combinations of a wave that's polarized along the x direction and a wave that's polarized along the y direction. take linear combinations of those two vectors and get any vector in the xy plane. If we do that, these are known as linear polarizations, as long as there's nothing complex going on here. Polarizations. Because ultimately, the electric field is pointing in some direction. And so it's going back and forth through the origin in that direction. Okay. Oscillating back and forth. We can do something a little bit fancier. We can also make circular polarizations. So with these linear polarizations, the wave may be going that direction, the electric field may be off in this direction, so it's just, the electric field is just oscillating from pointing down here to pointing up there and all the values in between. It's just oscillating back and forth that way. So it's oscillating along a line. Well, why can't we make the electric field go like this in a circle? Stay in the same direction of the wave going that, but the vector describing the electric field could go around in a circle. Why not? So that would be a circular polarization, and how do we do it? So we could do electric field is equal to some E naught, and I'll normalize things for some here. I can take x plus or minus, say, I, y hat. So the wave is going in the z direction. So if I just had this piece, it would be a vector in the x direction. If I just had this piece, it would be a vector in the y direction. I'm adding them together with a phase. And what's happening then, as the wave goes along, the electric field is going around in a circle. So for any given time, as you follow the wave in position, the electric field is going around. Or for any given point in space, as you watch in time, the electric field is just going around the circle. In the end, we take real parts as usual. And get the behavior that I just described. And so there are materials that have, so how do you produce a circular polarization? Well, there are different ways to do it. We'll look at one maybe on Tuesday. There are materials such as calcite that have different indices of refraction along different directions. And you can use that to make circular polarization. I'll describe that next time.